Hello, everyone, and welcome to our Econ seminar today. My name is Ivan Ortega, and it is my pleasure to introduce our speaker today, Joshua Laughner. Josh attended Penn State from 2018 to 2013, graduating with degrees in chemistry and music composition. He earned his PhD with Ron Cohen at UC Berkeley, where he developed a new version of the Berkeley high-resolution NO2 retrieval designed to accurately retrieve the day-to-day variations in urban NO2 plumes. After graduating from Berkeley in 2018, he started a postdoc at Caltech with Paul Weber, broadening his work to include greenhouse gas remote sensing. Today, we are using Slido to post questions, which you can ask at any time during the seminar. If you are not familiar with Slido, you can scroll down the webpage of the presentation where you are right now, and you can see the Slido interface at the bottom of the webpage. Questions will be passed to Josh at the end of the presentation. And thanks, Josh, and welcome, and take it away.
All right, thank you very much, Yvonne. Yeah, so today I'm going to talk to you actually about two projects. The first one is a first look at how NOx lifetime changed during the COVID-19 pandemic. And then the second one I'll bring up at the end is a more community tool project designed to respond to some of the challenges we face, really understanding how human behavior is driving changes in the atmosphere during the pandemic. I do want to mention that neither of these projects are actually my primary work. My primary research for the past 2 years has been on greenhouse gas retrievals for the TCON network. I will not talk about those today, but if that's something you're interested in, feel free to get in touch and I'm happy to talk about those. So for this talk, the first 3 sections are going to focus on the NOx lifetime work. I'll start with some background just to make sure we're all kind of thinking from the same starting point. And then I want to actually take a good bit of time and go through the methodology so that we're all comfortable with the strengths and weaknesses of this approach to actually interrogate NO2 lifetime from space-based instruments. Then we'll finish out that first project looking at some of the changes in NO2 lifetimes. And then at the end, for the last about 10 minutes, I'll shift gears and talk about this community tool set. So starting with the background, I obviously don't need to tell any of you that this pandemic has changed human behavior on a global scale, both through individual choice and governmental actions designed to limit the spread of the virus. What I'm showing on the left here are timelines of an index put together by a group at Oxford that is designed to summarize all sorts of different governmental policies put in place, things from school, business closures to travel restrictions, and represent that as a value from 0 for no restrictions to 100 for maximum. And you can see here I have plotted California, Colorado, the US as a whole, as well as China and Germany as interesting cases to look at because China is obviously on a different timeline from the rest of the world as the origin point of the virus. And Germany is an interesting case because through most of the summer, they were doing a very good job keeping the spread low enough to limit their restrictions. And if you look at this index, you can see that it probably jives pretty well with what you remember living in Colorado. Very limited restrictions up through about mid-March. And then in both California and Colorado, we had pretty strong restrictions for about a month that eased up going into summer. And then here in California, things started to tighten up in the winter. Looking at the country as a whole at the federal level, the restrictions never were as strong, but also didn't loosen up as much through the summer. China, on the other hand, has multiple waves of lockdowns. You can see the early initial lockdown, then a release, and then several more strict lockdowns. And Germany, you can see that we have this similar start to the US, but never as strict as either California or Colorado. And they actually managed to keep fairly loose restrictions until about December. Now, what I'm interested in is how NOx lifetime changed in urban areas. And of course, one of the big drivers of NOx emissions in cities is traffic. So what I'm plotting on the right here is a metric of driving mobility from Apple data. And each of these series represents a different region, and they're normalized so that 100% is mid-January. And so I have two California urban areas here, San Francisco in blue and Los Angeles in orange, the US as a whole in green, and then a global average in red. And this lines up pretty well with the restrictions in place. So we have a steep decrease in traffic throughout most of the world, but also in the Bay Area and LA, dropping to about 50% of mid-January levels in mid-March, and then recovering back to about 100% by midsummer, and then dropping off again. The US shows the same overall pattern, but actually goes over January levels in the summer. Unfortunately, because the Apple data set starts in 2020, it's hard to tell whether this is a seasonal thing, so people traveling during the summer, or if this is sort of a compensation for being trapped in our houses through most of March and April. But so this means that we have very dynamic month-to-month changes in NOx emissions. And I want to make clear, my purpose here isn't to rehash a lot of the really great work that's already been done looking at how emissions themselves have changed. So this is a figure from a preprint by Kazuo Miyazaki and his colleagues at JPL, where they used multi-constituent data assimilation to actually constrain the changes in this case, NOx emissions for countries across the globe. And I mean, this lines up pretty well with our intuition that, for instance, the US does not have much of a decrease in February, but has a strong decrease in March and April, and then emissions start to get a little bit closer to normal in May and June, whereas China has the strongest decrease in February and comes back to normal as we get into June. So what I'm more interested in is the knock-on effects of these emissions changes. So I've brought up this plot in the lower left, which is a plot of NOx lifetime on the y-axis versus NO2 column density on the x-axis. Each of the colored lines represents the relationship of lifetime to NO2 for a different VOC reactivity. And these are calculated from a pretty simple steady state model that takes into account OH, HO2, and RO2 as loss pathways for NOx. Now, if you're not used to thinking in terms of NO2 tropospheric column density, just to orient you, 1 times 10 to the 15th here is typically very clean air, and 10 times 10 to the 15th here is generally pretty polluted air. So we can see that the lifetime has this interesting nonlinear shape, and I've actually divided this plot into 3 regions based on the turning points in basically the derivative of lifetime with NO2. So in the right here, the one I've colored is dark gray and labeled region 3. That's your classic NOx suppressed region, where you have OH isn't increasing with NOx, and NOx is the primary reactant with OH. OH doesn't really have a chance to react with VOCs, and the primary loss route is through formation of nitric acid. Then getting into region 2, this is your classic NOx-limited regime, where NOx concentrations reduce enough that VOCs start to be competitive for reaction with OH. You can see that as we go to higher VOCR, the NOx concentration where we get into this regime moves to higher NOx concentrations. And as we move left through this, you start to see more and more loss of NOx through the alkyl nitrate pathway compared to the nitric acid pathway. And then actually in this plot, I've labeled a third region, region 1, which is where these lines turn over again and start decreasing. And this is where you get into such low NOx concentrations that NOx really can't be competitive with VOCs to react with OH. And so now your primary loss route is through alkyl nitrates. So in some previous work I published a little over a year ago with my PhD advisor, Ron Cohen, we showed using a similar technique as I'm going to talk about today, that if you consider the average chemistry in the plume as a whole for different US cities, all the US cities that we surveyed were in region 2, in the NOx-limited region by 2014. And so what I'm going to talk about today is my work to try and answer these 2 questions. So with the pandemic, of course, we have very sharp reductions in NOx emissions. How has the NOx lifetime responded to those COVID-induced emissions reductions? In particular, is the urban chemistry still in this NOx-limited regime, or are we slipping into this region 1, or has something else happened that we didn't expect? So now let me talk about the method that we're going to use here. So our goal here is to be able to get a plume average NO2 lifetime from space-based measurements. I'm going to be using TROPOMI today. I've used OMI for this in the past. And this approach, it was originally designed by Stefan Berle and his group back in 2011, and then refined by Luc Bollin, also in Ron's group, in 2013. And the basic idea here is a polar orbiting satellite like OMI or like TROPOMI will give you one snapshot of an urban NO2 plume each day, give or take. Sometimes you can get 2 snapshots if you're on the edge of the swath, but for the most part, you get 1 snapshot per day. And since we're interested in the chemistry, we want to make sure that we're really looking at the plume average. So what we do is we take each day's NO2 columns and rotate them so that the wind directions align. And you can use pretty much any reanalysis wind product for this. I'm using GeoSF-PIT, but I've used WRF in the past. Other people have used ERA5. It's pretty insensitive to the exact wind product you choose. But by aligning the wind directions, you make it so that when you then average across days, average in time, you're always averaging downwind pixels with downwind pixels and upwind pixels with upwind pixels. So effectively, you're not mixing the urban plume with background in your time averaging. Then the final step is to take this 2D plume average. So basically you can kind of think of this as a real world 2D plume model. And we integrate perpendicular to the wind direction to reduce the 2D column densities in moles per area to 1D line densities, which have units of moles per distance. And it's that 1D line density that we fit in order to extract the lifetime. Now, the function that you use to fit this is called an exponentially modified Gaussian. I'm not going to show the equation because, quite frankly, it's a mess and it doesn't really help the understanding. But conceptually, it is a 1D Gaussian function that represents your emission source convolved with an exponential decay and that convolution represents how chemical decay starts at every point in the Gaussian source. And so your downwind concentration really is the sum of all those slightly different chemical loss routes. So this function has 5 parameters that can be fit that include the amount of NO2 in the plume, the e-folding distance of the exponential decay, the midpoint and width of that Gaussian emission source, and a constant offset for the background NO2. Now for today, you really only have to worry about the 1/E distance. And in fact, we're not actually going to look at the distance directly, but we're going to convert that into lifetime. And the way we do that is simply to take the 1/E distance and divide it by the average wind speed over the time period that we're averaging. And that gives us our lifetime. We can also derive emissions from this method, and I'll bring those in right at the end. And the way that we do that is we take the A parameter, that's the amount of NO2 in the plume, and divide by the lifetime. So effectively, this is a simple mass balance assumption that the amount of NO2 in the plume is a sort of overall steady state, and the production and loss need to balance out. The other point I wanted to say here is we actually use the wind speed in a third way. So we use it to align the different days' downwind pixels. We use it to convert the 1/E distance to a lifetime. And we also use it to filter out days where the wind is too slow. If the wind is too slow, then the decay, the shape of the NO2 plume is governed more by the shape of the emission source than the chemical kinetics removing the NO2 downwind. So we only consider days where the average wind speed is greater than 3 meters per second. So this is an example. On the left are the wind-aligned column densities. You can notice that the X and Y axes are not longitude and latitude, but distance along the wind direction and distance across. And this is 1 month average for Paris. And you can see that, as you'd expect, there's a nice intense NO2 concentration over the city center, and then this sort of comet tail-like downwind plume. Now you'll notice it's not perfectly aligned with the x-axis here, which would be the case if the winds were perfect and the plume was perfect. But that's okay. That's actually another advantage of integrating perpendicular to the wind direction. So to go from the left plot to the right plot, we're basically adding up each vertical row of grid cells here. And that sum gives us the line densities, which are the black circles on the right. And so that helps to reduce the uncertainty introduced from this plume meandering. So on the right, you have the line densities as the black circles. You can see the y-axis is in units of moles per distance, and the x-axis is, again, distance along the wind direction. And then we're fitting with that exponentially modified Gaussian function, which is the gray line. Now, in particular, what we're interested in is how this downwind behavior changed between 2019 and 2020. And so I've added in the 2019 2020 line densities and fits. And you can see that for this month, the core plume decreased a little bit. But despite that, after you get about 75 kilometers downwind, there's actually more NO2 in 2020 than 2019. And if you just took this at face value, you could argue that, well, maybe this is that the wind was just faster on average in this month, and so it was affecting the NO2 downwind more efficiently. But remember, we then divide the characteristic e-folding distance by the wind speed, and that gives us our lifetime, which I have listed in the legend up here. And even accounting for any differences in wind speed, we can see that the lifetime actually doubled in this case between 2019 and 2020. So the first real step in applying this methodology is to choose the locations that we're interested in. And because I'd worked on US cities in the past, I already had sort of a dictionary of locations that this method would work well for. And so I brought those cities in the US forward for this study. But I also wanted to look at cities in Europe and Asia and Australia, and I'm adding some in South America and Africa as we speak. It's running on a computer here because, as we saw at the beginning, countries in different parts of the world had different responses to the virus. And so you can see I've marked some cities in Europe and Asia and Australia, and they're colored by the number of months that I was able to get a good fit of the line densities for. So it's the color bar represents the percent of months that were usable, and I break that down more so in the right-hand plot. So this lists all of the locations that I considered initially for this study. And the number of months is on the x-axis, and they're divided into 3 categories. The green bar represents the number of months that had really good quality fits. These are fits that there's nothing obviously wrong with, and we can expect that these are giving a good estimate of the plume average lifetime. The yellow bar indicate fits that aren't as good, but are still probably usable. And so for these results, I'm going to be using those fits to increase the statistics of the results. But you can also see that there's a lot of sites, a lot of months that are marked as bad. And these are fits that you can tell are giving a clearly biased lifetime. So what I'd like to do now is actually walk through a couple examples of reasons that I would exclude a fit, and then look at one example of a fit that is a very good quality. So here's our first example of a bad quality fit. This is the month average of Chicago in August 2019. And on the left, we have that same line density and fit plot that we saw previously. And on the right is this monthly average NO2 column densities. These are not wind aligned. So you'll notice that the X and Y axes are just longitude and latitude. And so one of the things I'm looking at in the NO2 column densities is whether or not the distribution of NO2 matches sort of a 2D Gaussian that's reasonably symmetric on both axes. Reason being, if it's not Gaussian, or if it's very asymmetric, then we're not going to be able to represent it well with a 1D Gaussian with a single width in the fitting function. Now, Chicago is pretty close to a 2D Gaussian, so that's fine. But when we look at the line densities, we see this double hump, this sort of camel line densities, where there's the initial decay downwind of the city center, but then there's this second hump at about 125 kilometers downwind. And you can see what that's doing to the fit. So the fit is trying to split the difference and line up with the main peak and the secondary peak. And it's dragging the fit up downwind, which is clearly biasing the lifetime high compared to the actual decay that we see and the line densities immediately following the city center. So this is an example of a fit that we would definitely exclude because the fit itself is biased in some obvious way. Now here's a second example. This is London in May 2019. And looking at the line densities, you can see that the fit is doing a really nice job of capturing the overall shape of the plume. But when we look at the NO2 on the right, we can see that it's very definitely not Gaussian, at least not a symmetrical 2D Gaussian. It has a much wider distribution in the east-west axis than the north-south axis. And the problem here is that as the wind direction shifts, that's effectively changing the width of our emission source. And if we're trying to line up all the days on the same plot, this is not going to work very well. We're going to be trying to fit some average effective width rather than the actual physical width. And there are ways we could deal with this. We could split up days with different wind directions. But for now, for this approach, we're going to exclude months like this where we have a very non-symmetrical Gaussian shape. And here's the third example. So this is Moscow, and I'm actually looking at both 2019 and 2020 here because this is something that I wasn't expecting. So I should say, for this work, I manually went through every single city, every single month, and decided based on the characteristics of the line densities in the NO2, which category to assign it to, good, okay, or bad. And one of the reasons that that has been really important is it gave me a chance to actually look at every single month and look for things like this that I never would have expected to have to change between 2019 and 2020. So looking at the line densities in the upper left, now we've got 2019 in black and 2020 in red. And the fits for both look fine. The fits are doing a good job of matching the line densities. But now I've got the 2020 or 2019 NO2 column densities in the lower left, the 2020 column densities in the lower right, and their difference in the top right. And you can see right away that there's been a really odd shift in where the NO2 is. So in 2019, it's about what you would expect, right? Here's Moscow. You've got nice NO2 plume right over the city, pretty concentrated. You've got a couple different downwind plumes going to the southwest and southeast. Maybe there's a little bit of a mountain here that's causing them to split. And that makes sense. But then when we look at 2020, it's changed completely. There's no NO2 over the city, and it's all spread out over 150 kilometers to the east of the city. Now, it's possible that this represents a change in chemistry if somehow the NO2 emissions from the city are being immediately transferred into some short-term chemical reservoir, advected to the east, and then re-released. But that seems pretty unlikely. I would suspect that this actually represents a shift in where the dominant emissions are coming from. If the city was completely locked down or a lot of people left the city during the height of the lockdown and went out into the country, that would seem like a more plausible explanation for what's going on here. As far as the fits go, the problem with this is we're not fitting the same lifetime or the same emission source between the 2 years. So although the individual lifetimes could still be usable, if we try and compare across years, we're not comparing apples to apples. So this is something else that we want to exclude for that reason. Finally, let me show you an example of a good quality fit, which conveniently is Denver in April 2019 and 2020. Again, we have the line densities in the upper left, and we can see that in both 2019 and 2020, we're able to very nicely fit the line densities with our EMG functions. There's maybe a little bit of a bump in the 2019 line densities, but you can see that the fit is really still lined up with the overall decay of the NO2 downwind there, so that's okay. And if we look at the column densities in the bottom two plots, you can see that we've got a nice, pretty symmetrical 2D Gaussian distribution. There's a clear decrease going into 2020. And if we look at the difference, we can see that it really is a decrease. There's no move, there's no shift in the spatial location of the NO2. So this is a great case study to use for looking at how the chemistry changed between the 2 years. All right, so now let me move on and actually look at some of the summary statistics of how lifetime changed. And to start, let's just look at the lifetime itself on the y-axis. So this is the lifetime fitted from the EMG functions versus the NO2, mean NO2 column density around the city center on the x-axis. And each of these points represents 1 month for one city. Each city has a different color and marker combination, but you don't really need to look for patterns with a given city right now. There's nothing, I promise you, there's nothing that really pops out in that respect. So one thing I did want to mention about the NO2 is that this is very specifically the mean NO2 from the wind-aligned monthly averages, the rotated monthly average NO2 columns. And the reason that that's important is because if you do the simple time averaging where you just average in lat-long space, that means that by its nature, you're sometimes averaging upwind pixels with downwind pixels. So a pixel to the, say, the northwest of the city could be upwind one day and downwind the next. But from the point of view of the chemistry in the plume, you care about the downwind concentrations. And so by taking the average over the wind rotated NO2 around the emission center, you're making sure that you always average the plume concentration, not the background concentration. The other thing I wanted to mention a little bit earlier, and I didn't get a chance to, is that the fact that we're able to look at the month by month lifetime is really quite amazing. So I worked with OMI on this sort of method before, and in order to get robust fits using OMI data, I needed to average 18 months worth of data. With TROPOMI, because the pixels are higher resolution and better able to peek through clouds, I'm able to get reasonably robust line densities with just a month of data, which is incredible and also really important because, as we saw at the beginning, your emissions are going to change quite substantially month to month. So you can't average over multiple months and get a detailed picture of how the chemistry changed. So let's come back to this plot. And as we're looking at this plot, we don't really see any particular trends of lifetime versus NO2. We're kind of spread out over all different NO2 concentrations. But if we think of this in terms of the prediction from the city-state model, remember, I would expect that most of these cities would be in under NOx-limited chemistry, where lifetime decreases with increasing NO2. And if we look at this plot, we can see that as we go to higher and higher NO2 column density, the maximum lifetime decreases. So even if we ignore these two DC points, which are at kind of suspiciously long lifetime, especially considering that DC lifetime is a little bit tricky to disentangle from Baltimore, we can see that going from these low column density months, which have maximum lifetimes in the range of 6 hours, to the more polluted months in cities like Moscow, where you've got a lot of NO2, the lifetime decreases, the maximum lifetime decreases and never really exceeds 2 hours. We've got maybe one example here, but there's this definite upper limit that seems to be imposed. So we can also maybe try and get at this by actually looking at the change from one year to the next. So I've just replotted this and colored it by year, and we can see, as you'd expect, that the NO2 decreases overall from 2019 to 2020. So the points have contracted on the x-axis. So if we were to actually pair these up with taking the 2019 month and location with its corresponding 2020 month and location, we can effectively compute a derivative of lifetime with NO2 and see where we are in this steady state model framework. So I've changed the plot on the left now, and on the y-axis is the change in lifetime, 2020 minus 2019. On the x-axis is the change in that average NO2. And we can see that there's kind of this loose pattern of many of the points being in quadrants 2 and 4, which correspond to an increase in lifetime for a decrease in NO2 or vice versa. And so that's a derivative, a negative derivative. And if we look at the steady state model, assuming that the only variable that changed between 2019 and 2020 is the NO2, that would tend to support most of these cities being in the NOx-limited regime, because that's the only place we get a negative derivative of lifetime with NO2. Now, we do have some that aren't in those two quadrants. We've got a bunch here in quadrant 3 and a few in quadrant 1. And we've actually got some pretty far outliers over here in quadrant 3. So it's possible that these different points represent either cities in region 1 or region 3, where you've got either very extremely NOx-limited or back into NOx-suppressed chemistry. But there's a couple things that I still have to look at here. So some of these points, the error bars in these might actually be big enough that the differences aren't statistically significant, and that's on my to-do list. And then these points over here, again, it's possible that these represent a shift into region 1 type chemistry, but I looked at these individual months, and there's some things that make me suspect the fits are not actually as robust as I'd hoped. So I need to reevaluate these points and decide whether or not they are really giving me a reliable lifetime metric. Now, we can, if we look at this, there's still a fair bit of scatter in this plot, but we can do one more transformation, which is to swap the x-axis from change in NO2 to change in emissions. And you can see that this really tightens up the relationship. And now we see that cities that, for whatever reason, had an increase in emissions have a decrease in lifetime. And for the most part, cities that had a decrease in emissions had an increase in lifetime, which again supports these cities being in NOx-limited chemistry. This then opens the question, what's the correct independent variable for this plot? Is it change in NO2 or change in emissions? And this is honestly still something I'm thinking about. There's arguments you could make for both. In favor of NO2, it really is the NO2 concentrations that drive the chemistry. It's the NO2 concentrations that determine the kinetics. And so that really is the physically meaningful variable from the point of view of the model, or from the point of view of interpreting the results. You do have to be a little bit careful, though, because when you have longer lifetimes, that means for the same emissions, there will be more NO2 in the plume. It will hang around for longer. And if you do your averaging incautiously, this can lead to some tricky covariances that you need to account for. On the other hand, in favor of emissions, really emissions are the independent variable. That's the knob that we would turn to change NOx lifetime in the atmosphere. We don't pluck NO2 molecules out of the atmosphere. We reduce the emissions and let the NO2 decrease naturally. But in this method, if you remember from several slides back, I said that the way that we compute the emissions is the plume amount divided by lifetime. that means that there is this implicit 1/x relationship between emissions and lifetime. And if I go back, you could argue that this is basically a 1/x relationship. And maybe that's just driven by how we determine the emissions mathematically. So at the moment, I would tend to favor NO2, especially because I think the way I averaged it means that the longer lifetime should not be impacting it. But this is something I have to think about some more. So let me wrap up this first project before moving on to the second one I want to talk about. I want to say that this work is all very preliminary. I've only really been looking at this for about the last month, but these early results do point to the plume average chemistry in most of these cities being NOx-limited. And we can imagine that has implications for what air quality strategies would be the most efficient in a future where we have sustainable lower NOx emissions at the levels we saw during the pandemic. There's still a lot I need to do here. Like I said, I need to do a full air analysis, update my air propagation code to follow the TROPOMI air budget instead of the OMI air budget, and check that these differences are actually statistically significant. And then after that, take those remaining data points that are significant and really dig in and compare them with a one box or a steady state model to really nail down what the driving factors are. And along those lines, one of the things that I would need to consider is how the production of HOX and VOC activity changed during 2020. There have been one or two papers I've seen in the last few weeks that have pointed out that there are significant changes in formaldehyde columns, especially in the first few months of 2020, which points to potential for changes in VOC reactivity, which mean that we now need to consider sort of a more a two-dimensional response of lifetime to these two factors. So for the last couple minutes, I would like to shift gears and talk about a project I worked on starting in the summer of 2020. And the motivating factor here was the Noah Diffenbaugh paper that came out early in the pandemic. And this was really a call to action, pointing out that this is a unique chance to see kind of a sneak preview of how the atmosphere is going to respond as we reduce our impact on it, as we reduce anthropogenic emissions. And one of the key points that was made in this paper is we need to be able to constrain how human behavior changed to understand that link between changes to society and changes to the atmosphere. And they pointed out that there's a lot of new data sets like cell phone GPS or social media that could potentially provide some really valuable insight. But these data are not easy to find, right? They're available from many, many different sources. They're in different data formats. And one of the action items, in a sense, was this idea of creating an open public repository that takes all of this different data on human behavior and homogenizes it into a simple format that's easy to find and easy to read. As valuable as this would be, there are, of course, a lot of challenges to using data from especially proprietary companies. There's what I would consider the scientific challenges, not so much in the sense of the science questions about the data, but just challenges to applying the data to scientific problems. And there are also what I would consider legal challenges. On the scientific side, these are mainly things that were brought up in the Diffenbaugh paper, things like having a standardized file format, having sufficient metadata to place that data in the correct context, just being able to find the data in the first place. This is not trivial. I spent way too long trying to find good data on electricity consumption in the US. And of course, we want the data to be citable and referenceable so that other scientists can build on our work. But there's also a lot of legal challenges with this, not insuperable, but definitely that pose an obstacle, especially because we're talking about a lot of data sets that are proprietary, things like the Google and Apple mobility data or the streetlight vehicle miles travel data are all products that they are probably not going to be super thrilled to just let someone else redistribute. And so those are the sorts of things we have to consider. If we want to have this centralized repo, can we get the right to redistribute someone else's proprietary data? How do we ensure proper attribution to them, not only in the sense of citing the usage of that data, which would be fairly straightforward, but if their system is set up to track the number of downloads of that data, how do we ensure that they receive credit for downloads through the central repo in such a way that they see that that data has value and they can continue to support it? And the third one is, what kind of liability are you assuming by having this central repository? For instance, one of the data sets that people have been interested in is the number of COVID cases or COVID deaths, which ultimately has to be derived from health data. And if an upstream provider mistakenly fails to completely anonymize this data and you redistribute it, what liability have you assumed by distributing improperly anonymized data? So what I tried to do is come up with an approach that lets us handle most, but not all, of this challenges to using it for science, using this data for science, and yet is designed in such a way that the legal issues simply don't arise. And the approach that we came up with is to not actually provide the data ourselves. Instead, we built a web portal where you could come, you could look up the data set, look up different data sets that you're interested in, and then instead of downloading the data from our site, we link to the original data provider. You download the data directly from the original provider, so we're not holding the data in any way. And then, in order to handle the challenge of getting it into a common format, we provide a Python package that, if you're working in Python, can be used to directly read the data into your notebook. And if you're not working in Python, you can use this to convert the data into a standardized format, which you can then read into MATLAB or R or IDL or your language of choice. So the portal is currently active. You can find it at the link in the title of this slide. And I just wanted to walk through very quickly some of the design of this portal. So on the left here, you can select the category or categories of data that you're interested in. And we've tried to emphasize data sets that are really about human activity more than the atmosphere. My feeling is that as atmospheric scientists, we're pretty good about knowing where to look for atmospheric measurements, but we're not as familiar with where to look for things like electricity consumption or traffic data. Then we've introduced a couple of other filters to try and make this easy to find data sets of the quality that you're interested in. So for instance, you can filter for data sets that have a certain range of spatial resolution. So in this case, I'm saying I want data sets that are at least resolved by state, not national or global. You can specify the spatial area that you want covered. You can similarly specify the range of temporal resolutions you're interested in and the time period it must contain. So for instance, this data must cover March to June 2020. You have the option to search by up to 4 keywords with a lot of control over how they're Boolean together. And then when you apply the filters, you get a list of the data sets that we have. And again, instead of having the actual data directly, there will be a link to the website where you can find that data. The second part to this is a Python package, which I have on my GitHub as an early version. Right now, this version is primarily useful for reading data into Python notebooks, and it can handle all 6 of these data sets. It can also convert the first and the fourth to netcdf files for use in other languages. So this is obviously a very big undertaking, and there's been a few of us involved, but I've been the main person trying to find the data sets and keep the Python package up to date. So I always like to ask for contributions in a couple different ways. The first is, if you visit the portal now, first of all, we now have the nice Caltech branding. And second of all, you'll see at the top, there's a row of buttons. the package button will take you to the GitHub Python package, but there's also this submit button. And this will take you to a Google form that is very, very short. Basically, it just asks for the link to a data set and whether or not you are a good person to contact about the data set, or it's just one that you found. And what this does for us is, if you find a data set that is, in your opinion, good for helping understand how human behavior changed during the pandemic, if you submit it to this forum, I can then go over it, add it to the portal, and do all the annotations for spatial resolution and all that we need. And so having a lot of people looking, not just actively, but if you find something you think is interesting and let us know, then we can share that with everyone else who uses this portal. And if you, for instance, know where it's good to get traffic data for Colorado, hint, hint, by all means, let me know. And because I'm really the only developer on the Python package right now, if anyone in the audience is a Python programmer and wants to help, or if you download the package, fork it, and you're thinking, boy, it would be nice if it did X or Y, feel free to contribute back to it, either with a pull request or ask to edit the repository directly. Definitely happy to have help on that. And with that, I want to say thank you to everyone for listening. I want to say a special thank you to my collaborators on the second project. Bart, Shell, and Dan helped with some of the early locating data sets and thinking through what kind of data sets we should try and find. And Irina did a really nice job putting the portal itself together. She did a very, very nice job there. My work is supported by NASA. I want to say a big thank you to my advisor, Paul. He's been very supportive and had lots of great advice over the last couple of years. And last but not least, I want to thank Yvonne for the invitation to speak to you today. And with that, I will be happy to answer questions that I'm sure are waiting for me in the Slido.
Thanks, Josh. That was great. Okay, maybe you can see it, but I will read it, the question. I can see some questions now. A question from Jim Schwab. How is the NO2 column distributed between the boundary layer, free troposphere, and above?
Yeah, so in urban areas, a vast majority of the NO2 is in the boundary layer. Probably, depending on the density of the urban area, it could be, anywhere from 2 or 3 to 10 times the column amount in the free troposphere. And generally about the same multiple of what's in the stratosphere. The good thing about this method, I will say, is since the free troposphere is generally more uniformly distributed, because the EMG fit includes that background term, the free troposphere effectively gets counted in the background. And so the plume itself that we're actually fitting is much more heavily weighted towards the boundary layer, which is the part that we care about for the urban lifetime.
Okay, I think we have more questions. Priya is asking, apologies if I missed it, Joshua, but at the end of the presentation, can you provide a link to the paper reviewing this research? I guess probably it's about the paper about the second part of the presentation. If you have that, you can just probably go to your presentation and we can see the paper.
Yeah, so I think probably the most important link is this one, the COVID Atmos link, COVID Atmos data links.caltech.edu. This is the link to the portal where you can find the data sets that we have collated so far, as well as the link to the GitHub site you can access through this. There isn't really a paper out on either of this yet.
I think Priya wants to know the paper, like in the introduction of the second part, there is a paper.
The Noah Diffenbaugh paper.
Yeah, that one. I think that's what I think.
Yeah, so if you search for Noah Diffenbaugh, it was in Nature Reviews Earth and Environment. I think it was around May this year. It was pretty easy to find.
Thank you. Now, question from Matt. The Moscow map you showed wasn't wind rotated, right? Could the 2020-2019 difference be a shift in mean wind direction?
That's right. It was not wind rotated. And I would have agreed that that would be a potential cause, except, sorry, I'm going to steal the screen back again. The thing that makes me think that is not the case is, let's see if I can get this full screen. The reason I think that's not the sole case is by just how much there's a total lack of NO2 over the city. So the white X here, if you can see that, marks the city center. And the fact that that is essentially background means that there can't be NOx emissions from the city unless it was just completely cloud covered. So I would say that, I guess the third option that we didn't really talk about is the problem might be that there was a lot of clouds to the west of the city in this month. But in that case, we shouldn't have NO2 column densities of 0. They should be nans and missing values because we aren't able to actually constrain them. So I don't think this is just due to wind direction. There's definitely a decrease in emissions. And since there's no emissions here, I don't think this is just advection from the city in a different wind direction.
Next question from Ben. Do you think TROPOMI could detect aircraft emissions? Is the detection limit could detect NO2 in the free troposphere? Or do you see differences close to the airports? Related questions will be there could be a change in the background close to the cities?
Oh, okay. Yeah. I don't think we can see aircraft emissions yet. The problem being, even though the TROPOMI pixels are smaller than OMI pixels, they're still, I think it's about 3 by 5 kilometers. And so a single aircraft track is going to be very diluted on that scale. So that's going to be hard to detect. We can certainly detect lightning emissions, but that's because lightning is going to happen over a broad storm front, and it's going to affect more of the pixel. Do you see differences close to airports? I haven't looked that closely. That's an interesting question. It's complicated by the fact that by their nature, airports are going to be transit hubs for ground transport as well. So you'd have to have a way to distinguish the aircraft emissions from the traffic emissions, which might be possible, but I'd have to think about more how to do that. The related question, could there be a change in background close to cities? Yes, and I had originally had that in the title because I saw what looked like some changes in the background concentration. There were a couple spots, especially in the Midwestern US and the Great Plains, where in 2020, there were elevated NO2 levels in kind of big area regions. The reason I didn't talk about that too much is I'm not sure yet if this is a real change in tropospheric background, maybe by soil NOx or some other process, or if this is just something to do with how the stratospheric separation works in the TROPOMI retrieval. So I have a plan to look at that, but I haven't had a chance to do that yet.
We have more questions from Helen. Do you have enough good months to look at how lifetime changes with season?
Ooh, potentially. I would, for that question, I would want to restrict myself to 2019, just because we saw in the first slide how quickly the traffic varied with month over the course of the pandemic as restrictions were tightened and then loosened. But yeah, I think you could. You would definitely want to have, well, okay. The caveat there is you'd really want to have the same location for all months. And with most locations, there are at least like a third of the months in a given year weren't usable. So that could be tricky. But I mean, OMI's had a good long lifetime. It's been up for 15 years. We'll hopefully be up there for many more, knock on wood. So once things get back to normal, get into the 2022, 2023, I bet we could do some pretty nice analysis with TROPOMI on seasonal lifetimes. Yeah.
Okay, we have more questions. Thanks for the nice presentation. A question from Behrus. What happens when you have multiple emission sources in your domain? Do you consider their effects?
Yeah, thank you. So this is always a challenge with this approach, right? Like I said, we have to assume that the emission source, well, for this approach, we assume the emission source is a single Gaussian shape. And something I didn't touch on in the part where I go through the methodology is that a big part of the sort of setup for the US cities was going through and really looking at different days, different time periods to try and screen out wind directions where you did have a second source downwind. So that bump in Chicago, I had already tried to exclude wind directions that would have caused that, and obviously didn't get all of them. So that's probably part of the reason that a lot of the cities outside the US tended to have fewer good months, because I have not yet gone through and done as rigorous a screening for exactly this, for multiple emission sources. Now, with that being said, there is an alternate approach that Fei Lu has reported on in the past, where instead of assuming a simple Gaussian shape for your emission source, you take line densities from slow wind days. Remember, we in this analysis, I only used days with wind speed faster than 3 meters per second. So what Fei has done is take the slow wind days, like 3 meters per second or less, when the line densities really represent the shape of the emission source. And then instead of convolving the exponential decay with the simple Gaussian, she will actually numerically convolve the exponential decay with those slow line densities. So that still assumes that you have a single lifetime for these multiple emission sources, but it allows you to deal with locations where you do have, maybe a central city and suburbs or industrial parks. And it was really valuable for looking at Chinese cities where you tend to have a lot of dense NOx sources. The downside to this method is you kind of need to consider each batch of wind directions separately. So she would divide she would place each day into one of 8 wind bins, so north, northwest, west, etc., and treat each one separately, which is fine, except it then multiplies by 8 the number of days you need to get a good, robust line density. And so that's definitely challenging for looking at these short, rapid changes in lifetime.
Okay, more questions. A question from Karen. Can you please elaborate on the reasons why the months were marked as bad for Mumbai? How about New Delhi? Thank you.
Yeah, I would have to look back at my notebooks. Part of it was a lot of the data there, I think, was screened out by the quality filters, either for clouds or aerosols. But this is exactly the one case where part of the problem might have also been I need to go back and filter out wind directions where there are competing sources. So I definitely, I will definitely go back and see if I can get better fits for the non-US cities. They definitely need some more attention to get some good fits and try and screen out some of these impacts. Paul and I were talking last week, might be able to do some interesting stuff with the night lights product to identify wind directions that we want to avoid, for instance. But I'll give it another shot in the next couple of months and see if we can get some better fits there.
Finally, I have one question, just quick question. So you say you apply this method for TROPOMI once a day. You have a snapshot of once per day. What do you think we will gain if we apply this method for, let's say, the future satellites like Tempo? So do you think we can gain something?
Yeah, absolutely. That, something that could be really interesting there is to look at the difference in chemistry between the morning rush hour and the evening rush hour. If you're thinking about health impacts, for instance, that might be one way to target the question of, maybe you can't reduce NOx emissions as fast as you would want, but if you tried to change, if you had policies to kind of induce businesses to open later or maybe open earlier and shift the rush hour to a different photochemical regime, would that improve your air quality by limiting some of the other reagents other than NOx? Obviously, you wouldn't be able to go into like pre-dawn times with Tempo, but absolutely, that could be a really interesting project.
Okay, thank you. We don't have more questions. That was very interesting, Josh.
Thank you.
Thank you so much for your time, your seminar.
And thank you for the invitation.
Yeah, thank you. Thanks everyone for joining.